Welcome to today's webinar, Collecting the Power. My name is Sarah Andrews with ABB's Wind Power team. I will be moderating today's webinar. Before we get started, I wanted to go over a few housekeeping items. All participant audio will be muted during the event. If you would like to ask a question during the event, please use the question box on the GoToWebinar panel. We will answer as many questions as possible at the end of the event. Please ask your question during the presentation so it will be available at the end. Today's webinar is being recorded. A link to the recording will be emailed to you following the event. Feel free to forward the link to people you know that could benefit from today's presentation. Today's webinar speakers are Dennis McKinley, the Director of Wind Power for ABB in North America. We also have Melvin Brown. Melvin is a Regional Marketing Manager for our Substations group with the ABB Power Systems group. To start, Dennis McKinley would like to open today's webinar with a few words about the wind power industry. Dennis?
Thank you for that, Sarah, and welcome to everybody out there that's listening and viewing. ABB went through the process and mapped out some of the major steps for a developer to look at, not including paperwork and PPAs, etc. And we call this the wind power value chain. We're hosting a series, we decided to host a series of 4 webinars on planning, collecting, connecting, and operating and maintaining wind farms. We're looking for feedback on this approach, and if it is of value to you or you want something more or different. Next slide. So just a quick overview. ABB has been in the industry for over 30 years. This is kind of a very visual showing of where ABB works in the industry. So we sell all major electrical components into the turbine OEMs, as well as what we call the electrical balance of plant down on the ground or offshore. We provide consulting services on the front end of projects, and we can get into a lot of different consulting services to help with grid optimization, connection into different networks, etc. Now let's go ahead and get started. Please take it away, Melvin.
Yes, in the design of the wind energy plants, the principal objective of the developer is to have the lowest levelized cost of energy. What that means is that that is the total price of generating the energy over the life of the project in today's dollars. Some of the key items that will have an impact on that is the selection of the wind turbine generator, location of the plant, the minimizing electrical losses, and designing of the balance of the plant for the system. Dale, take it away on the slides. In the consideration of the optimal design of the collector system, there's several things that we need to consider, and those would be whether the collector system is overhead on the ground, whether the point of interconnection, and also the location of the wind turbines. Next slide. A key component in the wind turbine generator step-up transformer selection is a key turbine in the level of cost of energy is a selection of the wind turbine step-up transformer. And the reason why that is a key component is that one of the items that we look to as far as reducing the electrical losses and improving the system efficiency. Next slide. A very important part of specifying the wind turbine step-up transformers is the efficiency of the transformers. Efficiency is very important because the higher the efficiency, the lower the losses in the system. Most standard distribution transformers have a efficiency of plus 98%. But what that means is that 2% of the losses, 2% of the efficiency is lost in generating power, which means that it affects the revenues of the plant. Next slide. There are two important losses that we should be looking at: no load losses and load losses. There's certain items that can affect the no load losses of the plant. One of the things that we look to is most standard distribution transformers are specified with silicon steel. Silicon steel can have low losses initially, but over the life of the transformers, the losses can worsen. So one of the things that we look at is coming up with a new type of transformer called Amorphous core. The Amorphous core transformers have very low losses. Losses could be as much as 40 to 70% of the losses of a standard transformer. However, what that means is that it means that the initial price of the transformer is a little more expensive, but you have low losses over the life of the transformer. That's why it's so important for specifiers of these type transformers to look at total ownership costs. I've seen a lot of jobs where a customer had worked very hard to get the price of the generator step-up transformers down by saving, $1,000 or $2,000 per transformer, but then spend upwards over $1 million over the life of the plant because they didn't consider the losses of the transformer. So one of the things that you want to look at is buying on total cost of ownership, which means that you want to make sure that you specify high efficiency transformers and also include a loss evaluation formula in the specifications. Next slide. When it comes to the collector system, you're dealing with very, very expensive equipment. You're looking at the transformer, the turbines, and the power transformer, which is part of the collector substation. These items will be very expensive, and so looking at the collector substation, which basically protects the feeder circuits, maintains the acceptable voltage levels, and really gets the power to the grid. The input into the collector substation would be the collector cables, and then the output is the power being delivered to the grid system. Therefore, when you're looking at a designer or an engineering firm that's going to design that collector substation, you want to make sure that you're dealing with a firm that has a lot of good experience dealing with local utilities and also independent system operators. Next slide. In the design process, we want to make sure that in the design process for these transformers, we want to make sure that we consider the losses of the system. The system losses and also the effects of various system disturbances like transients, dynamic overvoltages, harmonics, because these things can cause issues within the facility itself. Therefore, we want to make sure that we have factors that will mitigate those items. Next slide, please. Some of the causes of transients could be from switching cables, shunt capacitors, and so forth. Causes of breaker operating on the circuits, but some of the issues that we can utilize to mitigate this is introducing grounding transformers or fast-acting grounding switches. Next slide. Harmonics is a big indicator in the system. One of the things that we can use to mitigate the harmonics is the use of filter banks and capacitor banks and so forth. So we want to make sure that we mitigate those items. When it comes to the design of the substation normally operates at on the high side, whatever utility voltage is, looking at 69 kV, 115 up to 500 kV, and then on the low voltage side, medium voltage side, we're looking at voltages 15 kV and 46 kV. The medium voltage in the U.S. that's most prevalent is 34.5 kV. Although we have other voltages, for example, in Canada we may be using something else, some other voltage. But wind farms as they're being designed today are being operated at higher and higher voltages. And in the old days, you were dealing with low voltages like 69 and 115 kV, but now the plants are beginning very large, and it depends on what utility system that you're connecting to, that you can reach voltages up to 500 kV. Next slide. When it comes to the planning of the and design of substations, you want to make sure that you do some upfront work, feasibility studies, reliability studies, but also do your system studies. For example, short circuit studies make sure that you size the equipment properly, and also the cables, and also you want to look at arc flash studies, which is basically going to help protect the operators who have to work on the equipment. But the design process is fairly extensive. Typically, when you're looking at a substation, from the initial stage up to the final stage when the substation is actually built, you could be looking at 10 to 12 months. Also, you want to make sure that you do the preliminary engineering up front, which will help in the specification of the equipment, but also it will help in working with your contractors to make sure that you get the best pricing for the construction services. Next slide. Substations comes in various configurations. For example, you can have substations on the medium voltage side that the configuration is normally a single bus or sectionalizing bus. But on the higher side, you can have configurations like the single bus, the main and transfer bus, breaker and a half, and double breaker or double bus. Typically what happens is that the single bus costs the least, but provides the least reliability. And as you go to different buses, for example, like the segmented bus, you have a tiebreaker and two main breakers, which means that you split the main bus into two parts. And normally, the developer will also include a power transformer in that segmented bus design. The benefit of that is that you get increased reliability, availability, and you limit the short circuit ratings. Typically, the short circuit ratings of a wind plant is normally around 25 kA, but you can also minimize the continuous current rating. Some things that happens is that because wind plant sizes are increasing, it means that you're dealing with larger transformers. It means that the secondary current off those transformers can get very high. So using a segmented bus approach will also reduce the amount of continuous current rating that you have on the secondary of your transformers. Next slide. Next slide. There are many mistakes that are dealing with collector bus design. For example, you want to make sure that the reliability is the level that you need to ensure that you don't have a lot of operating and maintenance costs. And you want to make sure that you have lower downtime, which will affect the profitability of the plant. The key takeaways from today's webinar is you want to make sure that you engage an engineering firm early on in the process, and you want to make sure that you purchase your transformers based on a total ownership cost. You're going to have high initial costs, but you're going to have reduced operating costs over the life of the project. And you want to make sure that you supply transient and harmonic data when procuring your generator step-up transformers.
Thank you, Melvin. That was a very informative presentation. We'd like to thank you all for attending today's webinar. If you enjoyed today's webinar, I encourage you to consider signing up for other webinars in our Wind 4-part series. You can find more information at abb.com/us. We will now open the webinar for questions and answers. A reminder, if you would like to ask a question during the event, please just use the question box in the lower right-hand corner of your screen. We will answer as many questions as possible, and those we don't get to today, we will be sure to follow up on after the webinar. Melvin, the first question is for you. How early in the development process should the developer engage the engineering firm?
The developer should engage the engineering firm about 1 or 2 months after they have their wind resource information, and once they have the land leases in place. They want to make sure that they have early engagement so that they can get the most impact from the experience of the design firm.
Okay, thank you. What is the price difference for a generator step-up transformer with amorphous metal versus silicone steel?
Typically, the amorphous metal transformers is going to cost about approximately around 10% higher than a transformer with silicone steel, but you will more than offset that cost over the life of the transformer with the 40 to 70% improved losses that you will, lower losses that you will get.
Okay, the next question the person has asked, what is the typical lead time for the substation and generator step transformers?
Well, a typical substation, depending on the size of the plant, for example, plants that tend to be below 100 megawatts, the typical lead times would be around 7 to 8 months for completion of the substation. For the larger wind farms that are up, say, around 250 megawatts, the completion time would be around 10 to 12 months. As far as the generator step-up transformers, their lead times is normally anywhere from around 16 to 18 weeks.
Okay. I just want to remind everyone as these questions are coming in that in the lower right hand of your GoToMeeting panel is where you will find the option to ask these questions. The next question for you, Melvin, is what advantages to standardization, or what are the advantages to standardization of the substation?
The advantages of standardization is that you can have a substation that's completed in less time because in the standardization process, a lot of the engineering is already completed. The other benefit is that you can have lower construction cycles because you have engaged your construction resources in the standardization process. Now, there are some other items that you cannot change. For example, depending on where that wind farm is going to be located, you have to make sure that you comply with the grid code requirements of the local utility. So those are some of the items that's going to be project specific, and it's going to be with every project. And so in that case, you don't normally standardize on the local utility requirements because they change with every project.
Okay. The next question that I have is, what would be the schedule differences for the build on-site model versus the modular design?
Typically, you normally will have lower cycle times with substations that are modular designs. The cycle times will be shorter because normally the substations are completed earlier and they're going to ship to the site installed in a protected enclosure or building. So you're going to have less construction time. Typically on the built on-site substation, the equipment cycles may be a little shorter, but the construction cost is going to be higher, plus the construction time frame is going to be higher.
Okay. The next question that I have is, what is the biggest or maybe costliest mistake you have seen with these collection systems, if you can say it?
Actually, after the developer purchases the wind turbines, the biggest cost is normally in the balance of plant, which is going to be the collection system and the substation and so forth. I would say the biggest mistake that I've seen is, say, developers who undersize the collection system and therefore trying to cut costs. But then what happens after the plant is up and running, they have such huge losses in the system because they were not optimized that whatever cost benefit they got on the upfront cost part of the plant, they lost in the operation because sometimes you can get losses with an improperly designed construction system that could be up towards $1 million per year.
Wow. Okay. So the next question that I have coming in is, there seems to be a general negative opinion of the reliability of amorphous cores. Whether true or not, what assurances can you give that amorphous cores are reliable?
I guess based on our experience that we've had as a supplier of transformers with amorphous cores, that we have not seen the lower reliability. The transformers that we've seen and used have had very high reliability. But I think that if there's several things you can do, is that you can get some type of a warranty or extended warranty from the supplier of the transformers, and also make sure that you have loss evaluation and penalties built into it if the transformer doesn't perform as it was intended. So, for example, over the life of the transformer, if the losses is not what was guaranteed, then there will be a penalty involved, and the owner should be able to get some money back from the supplier.
Okay. The next question is, what is the availability of amorphous steel? Is it on allocation? Does this contribute to lead time extensions?
Our experience is that the lead times that, at least the transformers that we're building, there is no difference in lead times for the silicon steel versus the amorphous core transformers.
Okay. What is the best transformer option to near-coast substations connected to offshore wind farms?
Repeat that one more time.
What is the best transformer option to near-coast substations connected to offshore wind farms? So is there a specific transformer that they would need to use it for an offshore wind farm substation?
No, typically what we see is you have to make sure that if you're dealing with electrical equipment in general near the coast, where you're going to have corrosion from salt water, for example, you want to make sure that the material that the transformers is built in, or the painting system that the transformers manufacturer is going to use, is going to be able to hold up into that type of environment. So I would say that a liquid transformer that has the proper painting system, or you might want to specify a stainless steel enclosure, which is going to drive up the expense of the transformer, would be a better deal. Plus, you want to make sure that, since you're going to be near the coast, I would also utilize a fluid, environmentally friendly fluid, to be used inside the transformer. There are several on the market, for example, Biotemp, F-03, and so forth. I would not use mineral oil.
Okay. So there are a lot of questions coming in, and I think this might be because we had a few technical difficulties with the slides before. So this is great. This is a great time, Melvin, as long as you don't mind us drilling you with questions. So the next question that I have is, how much do local codes and regulations impact schedule and cost? Are there ways to reduce?
Well, the first thing that you want to do is you want to make sure that you dealing with a firm on the engineering side that has experience with the local utility codes, but also the regional system providers, the ISOs. But also you want to make sure that the firm is also experienced with the local codes, because sometimes the local codes are the ones that have the local jurisdiction could impact, have a direct impact on the schedule, and also the permitting process that you go through to get the plant involved. So I think that the best mitigating factor is to make sure that you have an engineering team in place who understands the utility codes and the local codes, and also the codes dealing with ANSI, IEEE, the National Fire Protection Code, and also the NEC. You want to make sure that you have a firm that understands that. That's, in my opinion, is the best mitigating factor. Because if you don't have that experienced firm in place, then yes, you will have schedule delays, you will have permitting delays, and you will not bring your plant online as intended. Because if you don't have the grid code compliance, for example, with the local utility will not allow you to connect to their system.
Okay. That was helpful. Is it true that small wind farms should be closer to the point of connection, in parentheses, with a distribution network? And is it true that those wind farms should be closer to the point of connection than bigger wind farms? And if so, is there anything that you could offer that would be helpful to understand why?
Well, I think wind farms in general you want to make sure that they're close to the point of interconnection. For example, if you have a wind farm that's especially the wind farm plus the substation, if it's not close to the point of interconnection, it's going to require you to have some type of transmission line, which means that the line could be anywhere from 1 mile to 20 miles, depending on how far you are from that transmission system. The second thing is that you want to make sure that you have done your homework up front to determine, based on your collection system and how it's configured, you want to make sure that you have the shortest possible runs of cable in the collection system so that you can keep your losses down to a minimum. The other thing is that if your collection system, for example, there are some studies that have been done that says that if you're dealing with a turbine, for example, that's operating at medium voltage, and you're dealing with a collection, you can use a collection system, for example, that may be at 15 kV versus 34.5 kV, if the point of interconnection in a wind farm is less than 3 miles apart. So I would say, yes, there is an impact on the location of the wind farm plant in regards to the point of interconnection.
Okay. Thank you. Hi, Melvin. How many cross-sections are there in a typical collector network, for example, a medium wind farm 30 to 50 megawatts? And how many cable cross-sections?
Typically what we find out is that we try to limit the collection circuits to around 20 to 25 megawatts per feeder. Okay, so based on that, you can calculate, depending on the size of the plant, you can calculate the number of cables that you need to run it. It could be 4-aught cable, or it could be 750 MCM cable, or 1,000 MCM cable, but basically you have to do your ampacity study to determine the current carrying capabilities, and then from that you can determine the number of cables that you're going to need for a 15 megawatt plant. But typically what you try to do is that you want to limit your cable feeds to 20 to 25 megawatts per feeder.
Thank you. The next question I have is, what percentage of wind turbine farm transformers are amorphous versus silicon?
I would say that today that the majority of the transformers that are being supplied, and this is when we say that we're talking about the wind turbine step-up transformers, the one that's located at the base of the turbine or just outside the turbine. I would say that the majority of those transformers that are built today are silicon steel transformers, not amorphous core transformers. Amorphous core transformers is something that has just started being pushed in the last few years by the manufacturers in an attempt to reduce the losses in the collection system.
Okay, thank you. Dennis, do you have any specific questions that you'd like to address here or ask Melvin?
Sure, thanks, Sarah. Melvin, just real quick, I apologize. We were kind of bouncing around on the slides there. We had some system errors, but you talked briefly about transients, dynamic overvoltages, harmonics, some of the system effects. Do you feel like you got through that clear enough, or did you want to highlight anything more in there?
Just the things that I want to highlight is that it's very important that you do the system studies initially up front. Because, for example, like I said before, you need a short circuit study to size your cable, size your components, determine your short circuit rating, and you need your grounding studies to determine what type of ground and system that you're going to use within the plant, and it affects your transformers, both the generator step-up transformer and the power transformers. So it is very important on buying equipment that you have the harmonic data present for the manufacturer to be on the transformer. Otherwise, what's going to happen is that you're going to get a transformer that may not be beneficial to the system in the sense that you're going to have a transformer that's going to have a short life span because the harmonic content was not properly provided to the manufacturer initially.
And that's great because, Melvin, I've talked to you and worked with you for quite a while now, and the biggest message that I think we try to get out to the market is it's a system-level approach. It's not an individual component approach.
That is correct. You got to have someone who has system and knowledge to understand the total system, dealing with the turbines, dealing with the collection system, the substation, the point of interconnect, dealing with the utilities, the local jurisdiction. You need to make sure that you have a firm that's going to be working with you start to finish. And also you're going to need somebody to help you through the permitting process, your environmental impact studies, dealing with the right-of-ways when you have transmission lines involved. So you're going to make sure that you have a firm that's well-established, lots of experience, and who can make sure that they point out a lot of improve reliability issues with you, and also make sure that they help you to lower the cost of the overall project.
Excellent. And again, you answered the questions earlier about local codes and regulations. One thing I was surprised you didn't hit on there was, I mean, basically you can save a lot of time with the paperwork going back and forth between the local utilities and the, and the wind farm itself as far as tests and all that go?
Yes. You want to make sure that that you have a firm that's going to be helpful to you initially when you get your, because there's a few studies that you have to do initially. You have to do your feasibility study, you have to do your system impact study, and that's going to determine what impacts to the utility system that you're going to have to change in order to connect that wind farm to that electrical system. Sometimes those changes are very simple. You can just have a line tap connection, or sometimes you have modifications at the point of interconnect, but also you have modifications at the substations above and below the point of interconnect. So you want to make sure that you have a firm that's very knowledgeable of the utility practices. The other thing, too, is that you're going to have to get a large generator interconnect agreement with the utility, and you want to have a firm that's going to help you through that process to make sure that you have the necessary information in place to do that. The other thing that you're going to have is that one of the things that sometimes people overlook is the amount of time that you go through permitting to get some of these plants completed. And you want to have a firm that knows the local requirements, knows the local jurisdiction, the counties and the cities and so forth, that's going to help you through that process.
Excellent. We just had another question come in, and again, just a reminder, if you've got additional questions, please submit them down on the bottom of your screen. Melvin, will your systems approach include some energy storage beyond the power transformer?
That depends. There are some there are plants that are located in some systems. For example, some plants that are located in the PJM system operators network that is going to require frequency regulation, for example. And when you have that, you're going to be looking at having battery energy storage systems that's going to be a part of that. So, but that means that you want to make sure that you have discussions with a utility to know exactly what needs to be done to connect the plant. If you had it up front, it's going to cost you less than if you had to do it after the plant has been completed.
Great. And I've got one last question for you, Melvin. First off, I think this has been great, but can you just wrap up once again? I mean, you've got a lot of experience with designing and installing these systems out in the field. what was your best experience of doing this, and highlight why that was?
Well, the best projects tend to be the projects that you have early engagement with a developer, and you were brought in as a member of the developer's team, and that you can work with them initially to get issues resolved. Because once you get the issues resolved in the design phase of a project, it tends to go smoothly. You tend to have less problems, and the projects tend to be connected on schedule. The projects that we typically have issues with are the projects where we don't have time to do the proper optimization of the system that we would need to, and therefore we haven't considered all the different alternatives, and we wind up having an issue where, for example, that the collection system may be undersized, or the substation has not taken into consideration the fact that there's a future expansion possibility. For example, we have a case where most of the wind farms that are built today are built in stages. For example, you may have a developer that's looking at building, say, a 300 megawatt wind farm, but it's going to be built in several different phases. The thing that you want to look at is that when it comes to the substation, for example, you want to make sure that you consider the full build-out of the plant, so that, for example, you can put in place, even though you only have one transformer to start, you can have a position in place where you have the second transformer foundation and transformer oil containment completed, or you can have the foundations for the breakers in place, or you can have the buildings where the switchgear is going to be included. You're going to have enough space to add future additions. What we tend to have sometimes is that customers who don't look at that, and then what happens when they come to that second phase, they spend a lot of rework in engineering and construction, and they wind up paying more money for that second phase than they would need to be if they had considered that in the original planning of the plant.
So your point, Melvin, is we prefer, the best approach is to do the studies as early on as you can up front with a system-wide approach. There are ways to remedy projects after they've gotten, certain distance down the road, but that's typically takes more time and obviously more money to go back in and potentially correct problems that weren't identified early on in the design phase.
That is correct. That is correct.
So we help on both ends, or we can help on both ends.
That is correct.
All right. We've got one more question that came in. What format do you prefer harmonic data when specifying a transformer, K rating, or the full harmonic study?
Well, we prefer the full harmonic study. Okay, that's the best thing to have is the full harmonic study up front. But a lot of cases, the developer may not have that information in place, and we wind up using the K factor. But I would say, as a preference, I would prefer the full harmonic study.
Okay. So I'd like to thank you, Melvin, and you as well, Dennis, and thank you everyone for attending today's webinar. We've wrapped up all the questions that have been submitted. If you think of any additional questions after this webinar, feel free to reach out to either Dennis or Melvin. We apologize for the slide issues that we had today. Every attendee will receive the final slides, so you guys can go over those that you missed. When you close the screen today, you will see a short survey of the event, and we really appreciate your feedback and comments. Thank you for attending the WIND webinar today, and have a great day.